Distributions are important because they provide an indication of the probability of an event occurring. Knowing that something comes from a normal distribution means that the analyst already has an idea of the shape and the fact that it's a bell curve, and a majority of the data will fall around the center point or the mean. There are a number of distributions that analysts should know, and this module goes through what some of them look like. And we're mostly focused with the shape of these curves than anything else. We just want to get a feel for when they might be used and what they kind of look like. We have a normal distribution, which is a bell curve. It's one of the more common ones. The uniform distribution, a binomial distribution, Poisson distribution, and exponential distribution. The normal distribution is the most commonly known distribution, and arguably the most important. It has the shape of the bell curve, and we know that 68% of the data points will fall within plus or minus 1 standard deviation of the mean. We also know that 95% will fall within 2 standard deviations, and 99.7% will fall within 3 standard deviations. So there's a lot of knowledge gained by knowing that a distribution is normal. More importantly, we'll see as you get more and more data regardless of the distribution, according to something called the central limit theorem, you will end up tending to have a normal distribution. And this is one of the things that's going to be easily seen when we look at the Poisson distribution. Some of the important concepts of the normal distribution are that it's bell-shaped, that 68% of the data lies within plus or minus 1 standard deviation from the mean, and another fact is that the median and mean are theoretically equal to each other, as well as the mode, and that's more of a theoretical concept with statistical distributions. Now, the uniform distribution can be considered kind of like a box, at least in its shape. In principle, the uniform distribution states that the probability of every event is equal, or uniform. When the chance of every event is equal, we have this thing called the uniform distribution. For example, if we have 10 cards, each card has an equal chance of being selected. It is a bounded probability distribution, which takes values between A and B, where A is less than B. And the probabilities of all the values are equal and can be continuous or discrete. Some important concepts of the uniform distribution are this. It is bounded with a lower limit A and an upper limit B. All probability values are generally equal, and it can be applied to both continuous or discrete random variables. The binomial distribution is a discrete random variable, and as its name indicates, it has 2 values. The 2 values are the probability of success and the probability of failure, denoted by P and 1 minus P respectively, or the probability of event A and the probability of event B if we don't have a success or failure. The most common example of a binomial distribution is a coin flip. Since there are only 2 events, heads and tails, each has a probability of 50%. So the concepts here are that it has a probability of P of success, or event A, and has a probability of 1 minus P of failure, or event B. And it is discrete, with only 2 events, A and B. Now, Poisson distributions help find the probabilities of counts. For example, the number of customers arriving in a store. A Poisson distribution is considered a discrete probability distribution since it deals with counts, numbers, and it's not continuous. The numbers between the counts don't mean anything. For example, if we wish to know the number of cars that cross an intersection or bridge at any given time, we'd be referring to the count of the cars, and the distribution would be Poisson. We associate the Poisson distribution with a count, which we call lambda. This lambda refers to the most likely count. And as lambda gets larger on the graph to the right, you can see how the curve begins to almost look normal. The green one is where lambda is 1. The red one is where lambda is 3. The blue one is lambda is 5. And as lambda is 10, it almost seems to have a bell curve to it. And this is one of the impacts of these law of large numbers in the central limit theorem. So important concepts here is that the Poisson distribution is discrete and refers to the counts or arrivals, and has a most likely number of events specified by lambda. Exponential distributions are similar to Poisson distributions. However, they are bounded continuous distributions which find the probability of times between arrivals. So whereas the Poisson distribution gave us the number of counts, the exponential distribution is going to describe the interval time between events or between counts. For example, the average time between customers' arrival in a store. Now, the chart to the right shows the distributions with different parameters for the rate of arrivals. Again, we'll use lambda for the rate, And notice how, as the lambda rate increases, the center depression begins to get deeper, it begins to bow inward. And that's one of the natures of this distribution. So it's related to the Poisson distribution, but it is continuous, and it has a rate which is denoted by lambda. There's also one interesting aspect of this, and that is that the rate is actually going to be 1 over the mean, or 1 over the average, which we'll see in the slides when we deal with the exponential distribution.